Okay, so I say, hey, what are all the different areas you're working on? How would we present that? How do we can we get a handle on what would that look like, and so forth? So we sat down with Ashok and we picked out one person that represented each of the first listed all the areas, and then picked like one person for each of the areas. So this is not I know the research spans not everybody who did internet protocols. They did just that Glenn's gonna work, but we want to pick something to see what that work looked like and how it evolved. And that is how this list came about. And yeah, that's pretty much the only two areas the area that's not represented here. That was the microprogramming that you can there you go. You can probably list half a dozen more if you wanted to. Okay. All right. So we'll not go into that. But anyway, this should give you all the way from 1980 to today. Faizan has not finished. He's hoping to finish PhD this year. And so he's still working on it. So you'll get a sense of the full range of the almost 50 years worth of work, right? And next. So as soon as I sent that request out, the questions started coming back. I think Jeff was the first one. He said right in the middle of the night, he said, so what do you want us to talk about? I said, well, I got to think about that. So came up with this framework where people think about and also we only give them 8 minutes. So I said, okay, you got 8 minutes to talk about, because 12, 9 times 9, 8, right? But yeah, that's about an hour and a half. So you got 8 minutes to talk about, and here are the kind of things we want to hear. This is general framework. Who or what inspired you to pursue topic of this PhD research? What was the summary or outcome of your PhD research? You can summarize it in 2 minutes. What was Professor Agrawala's role in that research? What was the legacy of your research? Who and what research applications did your research inspire at Maryland or in general? Research. What is the state of the research or state of art or state of work in the industry of that topic today? And if somebody is listening and wants to get inspiration about, hey, I'm looking for a research topic, would they be interesting to pursue this or not? So anyway, so that is a framework, and everything else is totally up to other people. All we can limit them is about 8 minutes or so, but it's totally at their liberty on how they want to talk about it. And our first speaker, as you saw from the list, is Jeff Moore. And I'll tell you a little about Jeff. Jeff and I have been staying in touch over the years. And Jeff, at least 3 times, he pulled me into different companies. Jeff has been CIO, CTO, chief scientist, chief architect. You got the idea. Those kind of positions he's taken in various industries, and he's still active doing that sort of stuff work, but mostly in large scale IT system design, development, integration kind of work. Jeff?
My topic was an area of workload characterization and projection. We're using clustering techniques and Markov models to describe computer workloads. As Ashok said a little bit earlier, I was interested in computer performance evaluation and systems performance, and the primary area then was large-scale computer acquisitions. The issue was you needed to test out the computers to make sure they're going to have the performance you needed, because you couldn't add a processor every week. It was like every 3 years, every 5 years. So you wanted a good idea what the system was going to do before you really got started, and therefore you needed to do benchmarks. Most people would take their largest job, here it is, they buy a computer to do that, and then it would fail miserably on the rest of their workload. As I said, we use cluster techniques. What that means was if you take a look at all the jobs and look at a number of features about each job, CPU use, IO use, whatever you like, you could look at it as the jobs being, rather than one big distribution is what people would do, as a mixture of several distributions of different types of work. And what clustering would do would allow you to cluster them so you find different groups of things that are really the same, and you can look at them statistically as a single entity to extract for a benchmark. Markov models is once we clustered the programs, knew what kind of programs are executing. A Markov model told you the sequences of execution and what the likelihood of going to one program was given that you were you were doing some of the others. Legacy of the research, clustering was unknown in the area of workload prior to when we were doing it. It was basically some multivariate statistical techniques and regression techniques and so forth. Now, if you go through most of the literature, any of the surveys or whatever, the k-means clustering is now one of the standard techniques. There have been NBS or NIST documents on benchmarking using clustering techniques. So I'd have to say it's one of the more sophisticated things and techniques in common use. However, they tend to use much simpler algorithms than what we did, just the straight k-means clustering. Problem with that is it gives you big round clusters. We allowed ours to vary in size and shape so that it could pick up if they're elliptical, whatever, which gave you a much better description of the workload. One of the things they're being used for today, since people aren't so much concerned with the gross level of the workload, because you can just keep adding multiple processors, was to look at the characteristics of what the work was doing. Because when you go to some place like Amazon, they'll give you like, I don't know, 24 processor families, each family with maybe a dozen or 24 different systems in it, each coincidentally with a different charge rate. So it's very helpful to know which one you're going to run best on. So one of the more common uses now is to select cloud processor types. Markov models, looking at sequences of the way people go through things now, is used more highly in web analytics. So at the Markov zero level, I can say, just whatever the probability is, now I can say, if I'm on this page, what's the probability of this page? If I was on this page before, what's the probabilities? So those are very useful in terms of modeling. What inspired that kind of research? As I said, I was interested in computer performance evaluation. As an undergraduate, I had taken what now would seem like a normal everyday course called Bionics and Robots. It was really an introduction to AI and so forth. It was a little bit less common in around 1970. You couldn't really build robots. You could learn about neural nets. You couldn't really build a useful one. It would take all the computer power at the university. So I recognized that early on. As is mentioned several times, although he was told to get out of the area of pattern recognition, Ashok had been doing a lot of work in the pattern recognition area. So therefore, both of us were well acquainted with the clustering and so forth. And looking at the workload problem and pattern recognition techniques, it looked like a real good match. And therefore, we started looking at that as an approach for workload characterizations and did a number of papers looking at all the different ways how workloads varied, how they varied by time, how they varied by location, how they varied by company, and so forth. All right, what is the state of the research today? Not much, it's being used, but most are very simple extensions. So for instance, when we did it, they were online systems, they're transaction processing system. There was no web. Clearly people are extended it to the web. I don't consider that to be a major extension. But I did find two actually interesting things that people were doing. One guy, he motivated by flocks of birds flying and how they follow one another. Rather than, normally in k-means, I take a look at a cluster, I take a look at a point, I put it in the cluster that's closest. What he says, well, the clusters are moving. Why don't I make use of the fact that they're moving? So if it was here at the beginning and it's moving in this direction, I'm less likely to put the ones behind it into it, more likely to put the elements in front of it, which would seem to be able to make it converge a whole lot quicker. Seems a very interesting use. The other thing that I found that was very interesting that people were doing, when you get to high performance computing, the large scale models, the ones that aren't done in computer science, that are done in astrophysics and computational chemistry, computational fluid dynamics, whatever, they run by a certain pattern. And that is, you spend a couple of weeks, couple of months, a lot of computational resources setting up a job. It runs for 3 weeks, it runs for a month, it runs forever, whatever, to get your results. And then you disappear and have to do analysis for 2-3 months on your results before you figure out that they weren't really what you wanted and you go back and start to modify the model. Someone is using machine learning to predict the future behavior of the jobs. What he says he's doing, and I'm not sure how successful, is to do clustering on the types of programs and whatever you originally submit, and based on that, predict what it is he thinks you're going to use, to therefore be able to figure out what types of processors and where on Amazon or whatever you should be going. As I say, I'm not sure it's going to work, but bring machine learning to the effort, why not? In terms of would it be relevant today, I don't see that much useful research really going on in that area now. That most of the projects I see or papers I see being written are more or less what I call how I spent my summer vacation papers. No, a guy has a job. He's told to do it. He writes it up as a paper. Yes, I work so-and-so. We had a big workload. We had a big problem. I clustered it. Here's what we found and so forth, which I'm sure is interesting to his bosses and so forth, but isn't what I would say really advances the state of the art in any kind of meaningful way. So I don't consider that a real fertile area for research. Now, the other thing, I have a very jaundiced view, because I was doing this 50 years ago, back in the 70s, where basically nothing had been done and the field was wide open. So you could just put a stake in the ground, this is my area, and not really have to worry about much of what had been done previously or whatever. I would suspect if you're to look at the topic today, if you're a student looking for a PhD topic, the areas that you'd have available to you would be much narrower and really need some work to really pull a good topic out of them.
Great, thank you, Jeff. Next up is Glenn Reichart. Glenn Reichart has been a technologist, businessman, CTO, computer networking, a security specialist, academic, educator. He's put many different hats on it. And he's working with the DARPA, he's worked with the Clinton White House. And one of the exciting things is Glenn has been inducted into the Internet Hall of Fame because of work that he did right here at the University of Maryland. Glenn?
Oh, thank you very much.
That's you. You brought a new different one?
Well, I just thought that I would click using this if I had something to plug into, but I don't, so I won't.
Okay, this is, you just click this, but pull this right there.
Yeah, okay, good enough. Thank you, and I'm going to timer here, so
excellent.
I'm going to keep
this
time.
is excellent. You have everybody bring in there.
I always finish on time when I know when time is. So I know when time is, I'm going to finish at 8 o'clock. Okay, so it's about time. Time is a key issue. You know this, lots of people in the room know about this. And I want to point out that it really is, can I use the enter key on the keyboard? Will that work? Yes. Okay. Who inspired me? Well, actually, I got inspired even before Ashok. My inspiration is, you recognize this gentleman?
Yeah, Dijkstra.
Yes, that's right. This is Edsger Dijkstra. And he did the mutual exclusion algorithm in 1965. And I said, this is really beautiful. But the problem is, I'm interested in these new things called networks, where you plug things together. And it didn't work unless you had your own shared atomic memory. So where's the algorithm for that? Right under the table. We can't find it. Maybe I should go and try to figure this out. Seems like a reasonable thing to do. So if you have a network, yeah, you can put one device in charge. How boring. I mean, that's what people tend to do these days. What if that thing fails? What if the group is dynamic? Well, we need a peer-to-peer solution. Peer-to-peer solution for mutual exclusion. So Agrawala and committee, we get together and say, this is a really important problem. If I can solve this problem, I get a PhD. Seems fair? Okay, so 9 months later, an algorithm, the Reichert-Agrawala algorithm. Many hours in his office. By the way, I don't know why he let me in his office for so many hours when I don't drink coffee. But aha, that was the reason. So my first refereed journal publication is on the cover of CACM. Wow. Okay, so that was the answer for that. And by the way, this is what happens if you search for it in Google Books. What is that? 4,750 results in Google Books. And by the way, you can get videos on this. So Ashok, if you ever need to get a refresher on how this works, you can just, I don't know what language this is presented. Oh, I guess it's in English. Yeah, he's got English titles there. Okay, so where did this go and what's happened to it? Well, most commercial systems do use coordinators like two-phase commit, Jim Gray, and so forth, really not peer-to-peer. But for true peer-to-peer, it has come back in the last couple of years. It has reappeared. It is called blockchain. If you take a look at the blockchain protocols, they go and they stick something like proof of work or proof of stake or something in addition to the Reichert-Agrawala algorithm, and you call it blockchain because they have to agree on who's going to put in the next block. And that means there has to be kind of a mutual exclusion-like thing that says only one of them puts in the next block. And in fact, they did botch it a little bit because in the blockchain algorithms for things like Bitcoin and Ethereum, you can have different people building different blocks and saying they're correct for some periods of time and they have to go back and recorrect them. It's really ugly, but I've decided not to work on that problem. It is really about time because remember, that was only 9 months. 9 months was not long enough to get a PhD. I mean, clearly a PhD student should work longer than 9 months, right? All faculty members agree, raise your hand. Yes, okay, so that's clearly right. So I wrote a second dissertation. And I'm very glad that Ashok and the committee made me do it because it got me thinking about even more important problems. And in fact, the more important problems are the ones that keep driving me today. So I'm very grateful for this second dissertation. It's on the impact of time in making network-wide decisions, where time is measured as the latency in delivering information. And my clock is timed out, so I no longer know if I'm on 8 minutes or not. But I'm going to try to stay on 8 minutes. You're going to tell me, Ashok, if I'm getting. This is a page from my dissertation on the second dissertation. It's all in one piece of paper. This is on like page 300 or something. There was when I said last night that he was a very good driver of work, it's a very long dissertation. So this is about how long it takes to get something decided in a network using one of the many algorithms that we explored. And so what you want is stay low on this graph. Lower is better. Let's see. I'm just going to yell and say, so obviously, if you can, you want to go on this line, the algorithm that's being used there. But after a while, that line actually gets worse than random choice. It becomes worse than random choice. And what's happening is in that region, you're using the information you're getting from other nodes, but it's become a dynamic system and it's begun to oscillate. And now it's become unstable and you're getting worse results than if you hadn't. So what you'd really like to do is you would like to follow that curve up to, but not including the random choice, and then smoothly move into the random choice. In fact, the rest of the dissertation is about how you should do that. But one of the things that I was never able to figure out, but Ashok being very determined, was what is the shape of that curve? Because it's not a straight line, it's not a catenary, it's not a quadratic, it's not a Bessel function, and neither of us could figure it out. So if somebody would like to do it, this is a fundamental information theory problem. Why in a network does that curve look like that? What are the mathematics behind it? We were never able to actually get that, and that's one of the jobs I leave for all of you to figure out. Okay, so it is once more about time being very critical. And of course, Maruti, which is named after the son of Pawan, the wind god, so runs as fast as the wind, hard real-time system. Levi, Tripathi, Carson, and Agrawala. Great work about time. Now I fast forward. US Ignite is my give back nonprofit. I spent a decade in government, a decade in academia, a decade in for-profit, and a decade in startups, roughly speaking. Not exactly, but pretty close. So after that, I said, what do I want to do that I haven't done before? And the answer was a nonprofit startup. So my nonprofit startup is called US Ignite. You can read what it does there. I know you can read faster than I can say it. We're working with all of these cities. We're applying advanced technologies of various kinds in these cities. There are about 22 employees right now at US Ignite. We fund this from about a third federal sources, about a third foundations, about a third the communities themselves or local foundations that they have. We work a lot with local and edge clouds because it's about time. You want everything to stay as local as possible. So we've established internet exchange points and other ways to minimize latency in each of these communities, because the latency really counts if you're doing things like remote surgery, online rehabilitation, and so forth. I also wanted to tell you a little bit about Reichert's law, which you may or may not have heard of, which says that if you take the growth in typical commercial internet speeds to the home and you plot them on a log graph, both the typical and the best offered, you get this pretty close to looking straight line, which is very interesting. So you may have heard of Moore's law. So this is Reichert's law. It has to do with typical communication speeds needed to the home. And it's equivalent to a compounding of 25% per year. So everyone who's still heading to go give people a minimum of 50 megabits down, 2 or 5 megabits back up. This will be completely insufficient in the next decade if this continues. And I don't see any reason that it's not going to continue at the moment. So this is the new Moore's law, perhaps. I'm not going to do this slide in the interest of time, but in some audiences, I talk about how time is important for these various applications. And of course, this is the application I really want to see. In order to do this, you have to have time accuracy of 1 millisecond for everybody and to be able to react in less than 10 milliseconds. And those are generous limits. It really should be a lot lower than that if you would like to see this. And this is necessary for a climate change mitigation, because if we don't brake and then reaccelerate, we can save lots of energy. We can also put lots more cars through the same traffic roads. So we can accommodate growth with less carbon impact, and we need to be able to do this. So can I take 2 minutes, or should I just quit right here? You tell me. Sure. Go ahead. Okay. Information theory could be part of the theory of everything. So I think quantum is really important. You may not know that I'm working with Ido Wachs here in the ECE and Marquis, the Maryland Quantum Institute. I'm on his advisory committee on how to use quantum networking and how to do quantum networking. Very exciting topic. And is information the fifth state of matter? And there's some really interesting notions that says that it is. So this is Melvin Vopspin of the University of Portsmouth. And he proposed that information is equivalent to mass and is equivalent to energy. It was mentioned this morning. I think Satish said that. And there is, of course, this is a famous equation from Einstein that shows the equivalence between mass and energy. And there's a speculative notion that maybe information is also related in that way, because we know that vast amounts of information cause very little change in math. And could that equivalence be another c squared? At least that's a very interesting thing to go and think about. And so over decades-long research, scientists have found that matter that collapses into a black hole leaves an imprint in the gravitational field, And so when the quantum correction is taken into account for quantum gravity, this imprint has been called quantum hair. And so things that fall into the black hole are not forgotten. They're represented in this quantum hair, in this little minute changes in the gravitational field for the black hole. This is known. So the way I think about this is that the universe never forgets. That's the implication here. And if the universe never forgets, and information theory is very important, then the universe will never forget Ashok Agrawala. Thanks.
So next up is Ron Larson. Ron Larson is the most recent place at home was University of Pittsburgh, where he was Dean and Professor of Information Systems. School of Information Sciences, right? And he has done phenomenal amount of stuff in his lifetime. He was when I got to know him, he used to be Mr. NASA. I remember Ron spent almost 13 years over
17.
17 years at NASA, and in various positions, an individual contributor to all the way to program manager and so forth. So Ron, all yours.
Thank you, Ashok. So hearing Jeff speak brought me back to some common threads between his research and how I used it. And I also discovered a tie into Glenn's second dissertation that I actually didn't know existed until you described it today. So what I'm going to reflect on is, you already heard some of this in abstract earlier today, but we're going to take it back to the early 1970s. I'm down the street at NASA Goddard working on the Space Flight Network Control Center as an assembly language programmer, a Fortran programmer for real-time systems that controlled the tracking network for Apollo missions and for an uncountable number of scientific missions. We used two system 360 model 75s to do that. They were redundant so that if one would go down, we'd still be up, because this was actually a 24/7 type of requirement, and it was real time. So we took things like reliability and resilience and performance extremely importantly at that time. So Jeff's work on workload characterization got me thinking, about how we might be able to move this whole technology forward in terms of some of the things that we were dealing with locally, just down the street. So as I mentioned, if you're in that environment, performance, resilience, reliability is extraordinarily important. In fact, it did happen occasionally that we'd be in the middle of a mission and both systems would be down. Bad thing in the middle of a scientific mission, or worse, an Apollo mission, when you've lost the whole thing and you've got to bring it back up in a hurry. So reliability was extremely important. But while all that was going on, there were other things that were beginning to shed a light on new directions beyond this traditional mainframe. The ARPANET, 4 nodes on the West Coast were suddenly connected to each other and shipping some messages back and forth. There were a number of labs across the country that were playing with the idea of local area networks. And DEC came out with their PDP-11 series, which seemed to transform the whole thinking about the marketplace of computing and ways to do that. So Ashok and I began to bounce some ideas around about how we might combine some of these technologies in ways that might influence the development and the evolution of the work I'm doing down the street on real-time high reliability performance systems. So one of the ones we looked at was, of course, you can't avoid Bob Metcalfe's work on the original Ethernet. I tend to think of this one as kind of the cocktail hour protocol. You wait for a break in the conversation and then you jump in. And if 2 people jump in at the same time, you back off and you wait for another break and you do it again. So that was kind of an interesting one. We didn't really fully understand the performance implications of it, but intuitively, it felt like an interesting possibility. Then Dave Farber out at UC Irvine had an alternate idea. He was developing a system he called the distributed computing system in 1973, based on a ring construction. And that was a kind of a lazy Susan communication idea. The lazy Susan is spinning, you put your message on there, it goes around, and whoever's addressed to pulls it off. Well, that was kind of an intriguing idea too, but we really didn't know how these might trade off against each other. Well, meanwhile, up the street, we discovered that NSA was sponsoring work on something called a common data buffer. They really didn't publish it, and Ashok and I almost got in trouble at a conference for even talking about it. We got kind of curtailed in the hallway, and literally they said, "How did you know about that?" But it did go public a couple of years later through NASA at the Launch Processing System. It's called a common data buffer. This was kind of the stew pot idea of communication. You throw it into a common area, and then people to whom it's addressed pull that stuff out. Well, so here we had 3 very different kind of concepts for how to just do communications, and the implications of how the performance of those communications was largely unknown. So this was a problem we're beginning to look at and think about, is it possible to connect a bunch of PDP-11s through a local area network in a super redundant, highly reliable fashion to provide mission support systems that we haven't seen before. So we wrote a paper on that, published it out at Goddard. That led to some interesting work, but among them, as we were trying to think about how do you get your hands around this class of problem, part of it was, well, what are you trying to do? What's the workload? So that was the first question, and that's where Jeff's work came in. How do we think about the workload that we're going to impose on these systems? Well, then the next set of questions is, what does the system look like? What's the demands on it? What kind of service distributions do you have? What kind of service time requirements do you have on this? How many service channels do you have? What's the organization of the service? What's the scheduling discipline you're going to use for controlling these? And ultimately, you're trying to establish what's the overall system capacity here. Well, Ashok and I started playing with some of the various ideas. Simulation seemed to be an interesting way to get a little bit insight, so we started there. We wrote a simulation system we called QNet Mod, and Karen was a co-author on that work also. So simulation gave us some insight into what how these systems might perform. But we were really interested in something that could provide a little bit more intuition. Analytic models were really ones that struck both of our fancies. Ashok being a control theorist, and it glommed onto that first, and we started exploring that. Didn't quite seem appropriate to the class of problem we're looking at because we had multiple decision makers, not just one control system. So we started looking at game theory. Well, the problem with game theory is you have competitive decision makers there. And this wasn't a competitive environment, this was a collaborative environment. So then we started looking at team theory, multiple decision makers to the shared common goal and how might we contribute to that. Ultimately, we settled on something that had been around for at least a century, queuing theory, to try to get an idea how we might schedule things through here and what the relative performance of these various systems might be. And from there, we went down into the rabbit hole. The interesting question to me at that time and to Ashok was, well, there are good analytic results for some classic single server Markov model queuing systems. The performance was pretty well established, but that's not what we have. We have multiple servers. And the multiple servers are operating at different speeds. So how do you control what's going on in a system with multiple servers operating at different speeds? That led us to the idea of threshold queuing that is illustrated in the upper right there. Of course, the idea is you use the fastest server first until some point where you start offloading some of the stuff to the next slower one and you continue to do that. Well, the math for that gets a little bit ugly fairly quickly, so we won't go into that. It took quite a while to work it out. But it did, as a result, result in a significantly large number of papers as a result. We did publish work on the performance of each of these communication systems and had some interesting conclusions about how to architect them. The legacy of it, we were pretty certain that the algorithm we put together for threshold queuing was optimal. It took 3 years and a couple of mathematicians up the road going towards Baltimore to prove that optimality, but they did it in 1984. Driven by Ashok's interest here and the invitation to come here today, I was curious when he asked, so what's the legacy here? He said, well, I don't know. So I took a look. So the work we did 40 years ago or more was still referenced 28 times in the past 7 months. I said, well, that's kind of surprising for a queuing theory result. And so it goes on. I went on to pursue it a little bit further, discovered that actually this whole domain is still remarkably active. There's a special issue coming out in the issue of mathematics called Recent Research in Queuing Theory and Stochastic Models. And they just are inviting papers that basically play on the other numbers of parameters. It's suppose it's not a Markov process. Suppose it's not that kind of a rivalry. They have different kinds of distributions. How about reliability? Suppose things break along the way. So all kinds of parameters you can play with. So it's apparently still a fairly active area, although I would argue it's probably remarkably slow moving also. So in closing, just to celebrate Ashok's work here, as has been pointed out over the past day or so, the number of things, the areas in which this gentleman has worked has been absolutely phenomenal. I owe my career to you, and I thank you.
So actually, Ron's work inspired my work. Actually, I remember a technical report, one TR about the network, trying to get a handle on the state of affairs and so forth. So maybe that might give me a starting point. So that actually led me through a different rabbit hole, but I ended up proving some optimality of certain algorithm that I invented and so forth in certain contexts. But anyway, thank you for your leadership and giving me the opportunity to sneak in as a number 8. So next up is TV Lakshman. TV Lakshman, he is a director at Nokia Bell Labs at Homedale, New Jersey. He's been there since you graduated, right? Pretty much that was your first job?
Yeah, pretty much.
Pretty much.
Various incarnations of AT&T at the time.
He's been phenomenal, yeah, except that used to be called AT&T back then.
Yeah.
Oh, I'm sorry, did I miss you? Oh, all right, well, when we come back to John. All right, well, I flipped my paper here. I didn't. Okay, so TV is he's been phenomenally successful at the labs. He's co-authored, besides all the stuff he does during the daytime, he's co-authored 3 books. He's got 58 patents to his name. Right. TV lecture.
Thanks, Ashok. Yeah, so I worked on decentralized consensus protocols, and sort of an interesting journey how I got there. So when I joined Ashok's group as the spring of 1983, as a research assistant and starting to sort of look into my PhD topics after having just passed the comms. I thought I was going to work on queuing because, as you heard, there's a long legacy of people who had worked on queuing, and I started off by reading Ashok Tereja's thesis, and I spent some time doing that and reading a whole bunch of other queuing papers. And then one day I was in Ashok's office and asking the standard graduate student question, what do I do? And Ashok said, hey, I think you should start looking at distributed decision-making, issues in distributed decision-making. He said, it's going to be a big issue. It's going to have a lot of potential, and maybe you should start looking. And then he pointed me to this paper on team decision theory that his advisor had written. And this was a paper, it's a fantastic paper, actually, written in from Proceedings of the IEEE. Can you hear me now? And it was, I think, Proceedings of IEEE in 1980, and it's a beautiful overview of what was going on in team decision theory circa 1980. And right there on that front page, there's a nice definition of what distributed consensus is all about. So there is information at different locations, each location having a different view of some ground truth, some underlying reality. And they all have to coordinate with each other to come up with a consensus on what the true picture is. So no one has the true picture. There's some unknown ground reality, which each one has a local view, and you sort of have to do some kind of a communication and coordination to get an idea what the ground truth is, and then you got to act on it to get some desired payoff. So that, in a sense, is what distributed consensus is. And this whole paper by Y.C. Ho was all about statistical methods, so looking at it from a purely probabilistic and sort of, I would say, controls kind of point of view. And my interests were more of algorithmic, and I wanted to do a little bit more of computer science kind of approach. So started reading more of the computer science literature at the time in coordination of decision-making in distributed systems. And this is 1983, so there was not a whole lot of papers at that time. There was clearly the sort of the seminal work that Glenn and Ashok had done on mutual exclusion. There was some other sort of really classic papers, Lamport's time clocks and synchronization in distributed systems. There was a very foundational paper by Dijkstra, termination detection of distributed computation, and some early papers on leader detection and leader election and so on. And this sort of was a very fascinating area. So I spent a lot of time reading all this stuff and eventually got into this, looking into this broad problem of distributed consensus. And there, once I started digging into it, sort of got interested in essentially quorum construction, because in most distributed consensus protocols, an essential component is building this voting quorums. And seemed like just looking into efficient ways of constructing these quorums is, would be a good thing to look at. And that sort of led me to this topic of message complexity, delay trade-offs, which is a topic of my in consensus, which is what I worked on. Okay. So what did we do? Essentially, we came up with a whole family of algorithms which essentially trade off message complexity with delay. So the longer you can afford to wait, the less messages you need to use. And we spent a lot of time proving a lot of optimality bounds there of how to do this. And the main challenge in doing many of these things is was essentially mostly combinatorial issues. So there were certain types of sets, which quorum sets, which had to be constructed, and they had to be intersecting and satisfying certain properties. So it turned out there were some nice ideas you could borrow from projective geometry, from a lot of graph theoretical techniques, like constructing sparse graphs of a given degree and diameter and so on. So I had a great intellectual time with that kind of stuff. And then applied it to a whole lot of instances of consensus. So blocking and non-blocking commit protocols, again, back to leader election, and more broadly, sort of computing certain classes of functions of distributed information when the arguments to the functions are at different places and everyone has to do the same kind of computation and finally have the same result everywhere. So we did that and published a whole bunch of papers. That was a summary of what I did. And then subsequently, Ashok and others at Maryland did a whole lot of subsequent work on it. One of his Ashok students, subsequent students, sort of extended all these things to a more robust kind of fault tolerance setting. There was work by Satish and one of his PhD students on sort of using these ideas to build a more efficient clock synchronization algorithm. And then there was Beverly Sanders, who was here from Harvard for a while and who kind of further worked on mutual exclusion, and a whole lot of other follow-up. I'm not being sort of comprehensive here. There was Mukesh Singhal who worked on this on a different sort of problems, but distributed systems problems. Sang-Hyuk Son, and a whole lot of others. And outside of Maryland, this is sort of a topic of much interest. So this whole issue of constructing efficient quorums has been a big topic of research way back in the late 80s, early 90s, and so on. And when I was putting these charts together, I was kind of looking at what's going on now, and sort of surprisingly found that a whole lot of references to some of those early papers as recent as 2022, and in a whole range of applications like UAVs, vehicular ad hoc networking, machine learning, crypto, and so on. So it's kind of interesting that after so many years, that's still kind of relevant. Okay, and finally, a few closing observations. So if you look at consensus protocols, so the late 70s and most of the 80s was essentially all about mostly academic work. A lot of theoretical work was done. And then there was the Paxos, Lamport's Paxos protocol, and a whole lot of derivatives from there sort of made it all very practical in systems, and it sort of migrated to industry and became foundational to distributed systems. And now it's like a building block for, the classical consensus was a building block for most distributed applications. But then along in 2008, circa, came a whole new impetus, which sort of lit fire on this field all over again. with the blockchain and Bitcoin and also Nakamoto's contribution here. So, and then the whole thing got fire all over again. The field has come alive. One of the things that happened is probabilistic consensus suddenly became much accepted. Even in crypto applications, it's all probabilistic consensus. And then there's this huge, the whole world of pure peer-to-peer applications that Glenn referred to. So there's a dream of making the whole world all, no centralization, no control, completely peer-to-peer. And that's a wonderful dream. And there's a huge amount of activity, both in sort of the research land, academic research, and startup land and industry. Around this whole blockchain-based ecosystem of Web 3.0, distributed apps, and of course, needless to say, crypto. And that's made the field absolutely relevant today all over again. And there's a huge number of, I think, work going on in how to make consensus address some of the shortcomings which these blockchain systems have, like very low throughput, extremely high energy consumption, and a whole lot of other things. So I think, amazingly, after 40 years of research, the whole field is as relevant today as it was then. And Ashok, your intuition that these problems are going to be important, which you said in 1983, certainly turned out to be true. Had a great time working on this with you. Thank you.
Thank you, Stevie. I'm going to go backward to John, and I see because you're John. Anyways, my fault there. John Hager has been a member of research staff at Institute of Defense Analysis for the last several years. Before that, he was vice president and general manager of Fujitsu Lab in America, and which was sponsored on Mind Lab. You know, one thing about Ashok is he keeps pulling us back in his orbit. We go away, and Ron was back here, Glenn was back here, John was like that. Yeah, so you got the idea. So which is a good thing. It's a really good thing. And so John was came back here from West Coast as part of the general manager of Fujitsu Lab. And before that, he used to California used to work at Rockwell Scientific. John.
Okay, thanks, Ashok. So I'm going to take a little different tack than the others because I don't take direction that well. So the framework kind of went by the wayside. But I will talk about my experience as a grad student and how that had affected my career in computer science R&D for over 40 years in sort of unpredictable ways, at least that I couldn't predict at the time I was in grad school. So I started out in grad school in '76, and I was hired as a research assistant by Dr. Agrawala to work on the project that Ron described with NASA to do an evaluation and a comparative study of various local area networking technologies. And if you think back to that time, I think as Ron alluded to, it was early days for loosely coupled distributed computing, early days for local area networks. Ethernet had just come out for a couple of years. And so among the graduate students and Professor Agrawala, we were asking sort of basic questions at the time that now seem obvious to current practitioners. Things like, why would computers ever want to talk to each other? Or are local area networks fast enough? You know, which protocol is going to work out the best? What kind of applications could possibly use communicating computers? So kind of very fundamental questions at the time. And that started my interest in distributed computing that's lasted throughout my career. So as my research work in graduate school, I started to look into models for predicting the performance of distributed systems that explicitly took into account the processing, the networking, and the software that was running on those systems. And so while doing that, as a graduate student, I learned some basic tools for doing research that helped me throughout the rest of my career. The first was a good foundation in queuing theory, and the second was how to do discrete event simulations. And I put a couple of books on the side that had a big impact on me at the time. Was Kleinrock's queuing theory book, volume 1 and 2, which was like the Bible at the time. And then SimScript 2.5, which was the simulation language we used at the time, which probably no one's heard of by now. But anyway, it was an important tool for this work. So as I said, I want to track my career a little bit. And so my first job after I got out of school in '81, I took a job with an aerospace company that was building a packet radio network for commercial airlines. It's one of the first packet radio networks. And one of the first tasks I had at that corporation was to do a performance model of that network. And so we built a little simple queuing model of the packet radio network. And we showed that the mini computers that they had bought to do the message processing were not powerful enough to do the job. So this immediately made me unpopular person at this company. So anyway, I continued with that kind of work, moved on to other companies, and spent next several years doing discrete event simulations at Rockwell of increasingly complicated systems, starting out with communication systems, command and control systems, data centers, and so on for several years. And it became a bit of a challenge to get enough computing power to actually run these simulations. So we began to investigate using distributed computing to actually run the simulations. And so I spent the next several years building distributed simulation systems using optimistic processing methodologies. And we built a large-scale simulation system that was used for almost a dozen years to do missile defense modeling. And so also during that time, I was fortunate enough to get involved with a research project on industrial automation, where we were trying to push the limits of distributed processing and say what would happen if you put a processor and networking capability on every sensor and actuator in the factory system. So we were trying to see if we could increase the performance, the reliability, the adaptability of the factory automation systems of that time. And so we were pretty successful in working with that technology. And that led pretty naturally into looking into putting wireless communications onto those sensor networks. And that led to a fairly intense period of 7 or 8 years working with DARPA and other universities on distributed sensor networks. And after about the year 2000, it turned out that Professor Agrawala again had a big impact on my career. And I was at the time working at JPL, looking at sensor networks for planetary exploration. And Professor Agrawala was in communication with Fujitsu Labs, who was thinking about opening a research lab, as he mentioned, on the East Coast. Fujitsu is a large, at the time, Fortune 50 Japanese IT company, and had quite a bit of influence in the world IT market. Anyway, they wanted to start a research lab on the East Coast. Ashok told them to talk to me, and they convinced me to come back here as director of that lab, which lasted about another decade. While at that lab, we worked a bit on smart systems, smart offices, smart homes, smart cars, et cetera. And the mode of operation was to work with the Mind Lab and to collaborate with grad students from the Mind Lab and also other students at the university for research and internship positions and so on. And we literally walked through burning buildings during that time. It was a very productive research period, in my opinion. It also got into looking at security and trusted systems, as that became extremely important for developing these smart systems. So after that lab closed, about 2010, I moved over to the Institute for Defense Analyses, where I'm involved in a variety of projects of interest, still trying to maintain activities in distributed computing and occasionally getting to work on projects that have a connection to the work done earlier in my career. So what I see as the future for modeling distributed systems, I think there's a big push now for digital engineering and digital twins, where you're building very high fidelity models of cyber physical systems. And those models need to be integrated with what I call attribute models. Attribute models being performance models, security models, reliability models, and so on, so that when there's a change in the high fidelity model, it's automatically reflected in all of the other models that are built around that central hi-fi model. And also, so I think there's a lot of research to be done in that area still. Also, I think in general, with the emergence of various new computing paradigms, there's lots of opportunities to develop new and improved models to capture the attributes of those computing systems. So I just want to close with an observation for the grad students. You know, when you're in grad school, learn some tools and some techniques and make some good friends, and you'll never know what doors will open in your career. Thank you.
Thank you, John.
All right.
Next up is John McCloskey. John is currently a senior cloud networking architect at Huawei. Is that right? Did I get it right?
Yeah, I was
Huawei,
but not IBM. I was at IBM.
John's going to tell you. I'm saying that you're a senior network architect at Huawei.
No, I retired from Huawei. That was a while back. That's right. Except the elk and the deer and the moose. There we go. Thanks. So I'm going to take a cue from the previous speaker and go a little bit off topic, but not much. But the emphasis, I think I want to say is, when I came into Maryland and talked to Ashok, that was the signpost I was looking for. And he provided direction in every single way I could possibly imagine. Very much indebted to him. My research wasn't inspired by Maryland, it was actually inspired because of what was going on at IBM at the time back in 1979 or 80. IBM was, mainframes were big deals and systems network architecture was the system. At the time, IBM owned the networking world in the commercial area. Over 50,000 commercial SNA networks around the world at the time. Huge amount of money involved in it. There was always this problem with when they started putting these networks in. The main, customer would have a response time of a second, and the next an hour later it'd be 10 seconds, 20 seconds. They'd get all excited. No one knew what was going on. The mainframe guys would blame the networking guys. I'm the networking guys. We didn't know what was going on either. We blamed the mainframe guys. So there's a lot of finger pointing. After a while, I figured out we got to fix this thing because products were actually piling up on loading docks outside of customers that wouldn't install them because they didn't know how to operate them. It's classic problems. I was part of field engineering, which is interesting. I'm in the repair business, so to speak. As a kid, I used to carry a tool bag around and actually fix mainframes, believe it or not, when I was going to college. and also printers. I've seen everything. They thought I was really good at the hardware stuff, so they made me a software engineer. And I started working on that stuff. So networking was a big focus. There was mysterious response time issues and problems grew, and the idea of an entire system that a company could actually utilize to make money, save money, or gain a competitive advantage, because that's why companies bought technology. So it was really a big mystery. IBM opened a system center here, invested at the time, I think it was $20 million in a very opulent building over here in Gaithersburg. And the whole idea was to get people from different disciplines together, write guides on how to hook up networks and databases and all that other stuff put together. So we had experts all across. You talk about professors with egos, you would see nothing, get to these things. Everybody had their idea how things should work, right? They've always optimized their products, right? So it's very interesting. The net result of this stuff is when you worked on anything, you got dumps and traces. So if you look at a dump back in the old days, it might have been 10, 20 pages of hexadecimal that was interpreted on the side. And over time, that 10 or 20 pages came out to be 10 or 20 feet. I mean, you literally couldn't do anything with it. It was data, it wasn't information. That triggered another effort inside IBM. We call it information collection architecture, because after we got all the data, and this is just a dump of what was going on in the memory, when you go to the network and start collecting packet information, timing between packet sizes, whether congestion indicators were on, all those other things, try to put together a story of what was going on out there was very, very difficult. So there's this optimality question was a big question at the time. So I would liken it to a sports car. You're driving, you spend $5 million in IBM products on a sports car, you're driving down the road at 30 miles an hour with your pedal to the metal, so to speak. And you're really happy until someone passes you going 80 miles an hour. And now being happy, you're now unhappy because now you got a yardstick to understand what optimality is. And even at that point, that was, your system can run better, but what was what was in fact the capability of the systems, capacity planning kind of stuff. So we invented some algorithms to feed not only problem determination and capacity planning inside IBM at the time. We also developed what I call state vectors that we put together. And they were depending on what was going on in the network, the virtual circuit paths in the network. And this is where I got involved with Dr. Agrawala, because we're looking at this stuff. I looked at the network management. What I found is that if I looked at network research at the time, steady state behavior and simplifying assumptions, it didn't help me fix anything for customers. And I did have backing financially inside IBM because IBM wanted the problem solved and the customers were banging on IBM to get it solved. So they sent me to school and they support the efforts and stuff because I told them to find some answers out here at the university, which we did. So when I looked around in the network data, I possibly looked at 1,000 network traces over my time at IBM, and it's probably underestimate. I never saw any Poisson or exponential unicorns running around in the data. Everything was always deterministic. You could see dispatching taking place. Disk head movements, for example, would reflect itself in some of the actual bulk data transfers that you see out there. So I focused on looking at the feedback paths and the actual physical characteristics of the path. So instead of taking steady state stuff, we looked at dynamic behavior. So the summary of the research basically turned out to be the fact that where I came up with Ashok's help, everything is a we, but I realized Ashok was a big factor and influence in guiding me because he did everything with the signposts for sure. So I look at this, it was a new deterministic analysis technique for the study of window protocols. Second thing is we did a precise description of the dynamic window protocol behavior, and we did an analysis of it based on characteristics of the optimal settings, so to speak, if you want to talk about that, and physical path characteristics, so it hadn't been done at that point in time. Everyone was focused on the mathematics. I'm actually trying to do something out there so customers aren't killing me out in the real world and I could go home. Ashok likes to tell a story, and it is true, actually, that I go out to customers, but I didn't have a letter to actually tell them over the phone, hold on to this guy till your problem's fixed. So if I wanted to go home and see my family, I had to take care of it. It was very interesting. So Professor Agrawala's role in the research is pretty much everything. I mean, it was a fantastic help. The fascinating thing I found is that we went into this area of network repair for a lot of, I was a repairman for a lot of practical purposes. And trying to fix this stuff means you need to understand what normal behavior is, what abnormal behavior you're looking at. So you have someone says, this is what it's supposed to do, and here's what it does. And getting descriptions of those two things are very, very difficult. And I think that's what a lot of research still takes place today in computer science. You get a complicated system. How the hell is it supposed to operate, right? So you compare the two, you look at the delta and find out how do you get from where you are here to where it's supposed to be. And generally that could be capacity, newer memory, bigger line costs in those days. So we're looking at all this stuff here, and we developed state vectors about what was going on in the system. So we actually use these systems of vectors as an input to an expert system that we had built with a knowledge base, all that stuff. It was the IBM research told me at the time it was the only expert system in operation on the planet that actually made money. So we would literally go out to customers, run traces, and use the information into the system. We would tell them what the parameters were wrong, whether they need more capacity, those kinds of things. You got to realize in those days, IBM networking and systems network architecture was economics. The trouble is technology people don't focus on economics. And I fell into the same trap because SNA is not around anymore, right? As a matter of fact, if you look at information collection architecture that we're actually building, so we could skip the step of pre-processing. Paul Hershey got a PhD on that over here at University of Dr. Celio. I think you're an advisor as well. We actually built technology to do that. Of course, we applied it to Token Ring, so we're really good at picking the technology that's going to win. When I got to Cisco, I focused on WiMAX. So there's another one. So if you want to know what's going to die in the future technology-wise, let me tell you what I'm working on. We can take it from there. So IBM didn't see any financial benefits to the internet at the time because it was all protecting customers' investment in the technology that IBM sold them and the phone company. Got to realize a T1 link, this is 1,544 bits per second at the time, depending on the length, could cost you up to $30,000 a month. Okay, it was a big deal. Right now, you're getting 100 megabits in your house for $30 a month, right? So if you look at this, nobody cares. With 100 megabits, you can waste 50 or 60, don't care, as long as response time is appropriate and you can get the work done. And phone companies not charging you a delta, whether you get 50 or 100, they just give you 100. Things are bumping up, same price. They just want you to keep the price up. So you go through all this stuff here, and IBM didn't see that benefits and got themselves basically out of the networking business because the economics of it. At that point in time, I moved over to Cisco, and I started working at Cisco Systems, and I got involved in WiMAX. That didn't go anywhere. Then I did standards for a while. Finally, I left Cisco. We became the chief software architect at Motorola. And what we're trying to do is, how do we take all the different software technology pieces and look at them as parts and have people assemble them? To tell you an idea, there's opportunities out there for clever people if you want to solve real world problems with money impacts. In Motorola at the time, we had 4 major divisions. And if you look at the software in a cell phone and the software in a set-top box, it's 95% the same thing. But everybody's writing the software over and over again. TCP/IP stacks in Motorola, there were 17 at the time. 4 of them we bought from an outside vendors. I mean, it was almost criminal how they waste money. So we started putting all this together, and executives made the wrong decisions about where the market was going to go, and then Motorola just fell apart. So I went up working at Huawei doing analysis on, again, TCP/IP and virtual circuits. And they were focused, my work in Huawei is mostly focused on intellectual property. So I was helping them define what products would do in the future and protecting that little, what do you call evolutionary step forward in each of the individual products. So I learned after a number of hard knocks that if you get into a situation in a private company or a big company, whatever, commercial, that if you attach yourself to a product that's making money and you're a part of the evolution of the product improvements, you write intellectual property and things like that, you have a very successful career, and you can run off in all different directions for other things as long as you pay attention to bread and butter at home. So that's what I learned. If I look at the research I had done, I still believe today all networks are mostly deterministic. I suspect they are. The research I put together, when you read it, you could take the state vectors that'll be defined there by how you build a model, and you can create expert systems on any number of systems out there. It doesn't have to be SNA. We actually started on a TCP/IP one, but then IBM decided that really didn't want to go there. So that work stopped. When you have to support a family, a wife, kids, and stuff like that, you tend to do what they tell you, even though you'd like to continue with your research, okay? There's no option there. You guys have some flexibility down here. You might find another sponsor. If I have to find another sponsor, I get another job. And basically, I did that a number of times. So if you're looking at networks, they're all deterministic. You could extend the research with allowing like packet losses, looking at non-work conserving kinds of activities out there. Research could be extended instead of doing bit and byte models to do chip models, where a clock cycle sends 64 bits, 1,024 bits per clock or whatever, based on phases and everything else that takes place. There's a lot of fascinating things out there that can extend the research and get an idea of what's going on. The economic challenge turns out to be, does somebody really care? If you've got a gigabit network running at 3% all the time, which is most of the backbone links in the internet, who gives a damn whether it's dropping packets or not? It's not worth it. It's like, do you want to manage your refrigerator? No, you just want to make sure you fix it when it goes bad as soon as possible. But managing it, you could care less. So I kind of learned that over the years of look at things, and you're trying to sell customers systems management types of things. Nobody really cares about that except for you who are inventing the management stuff. Your overhead, to be quite honest with you. Customers don't care either because money solves their problem, and it's cheaper to add another line capacity than it is to hire you. So as you see the evolution of technology, what's going place, the fact that things are so cheap, so fast, and so capable makes a big difference on where you want to focus on your research and what you might want to do if you want to be successful in the future and make money. So that's kind of what a little bit of my story where I went to. But you can certainly take what I've done and you can look at these kinds of things because you could figure out from path analysis what's going on in the network. We found really fascinating things. We even saw that in early TCP networks at the time, is that when you get vectors of information, you could assign vector states based on values in a relationship to other values in the vector you had. For example, packet sizes versus timing between packets, those kinds of things, whether congestion indicators are changing or windows. So each of these represent a state, and you can get a signature of a state transition diagram that says you've got a buffer pool problem in these kind of boxes. It's really, really simple. So you can actually make an expert system an expert, but the key part is how clever you are with the state variables. If you try to put everything about your products and stuff into a knowledge base and think you're going to bang up against it and get an answer, you're going to be really frustrated. So the way you propose the problem and you put it together will give you some real success. And you can take this kind of research and extend that in that direction, because I think looking at deterministic activities in the network, it's all full of deterministic activities. The question I always wonder, if you get enough deterministic cycles out there of all different things, does it become random? So I don't know. So yeah. Okay. It does become random? Okay. We have to convince some customers I have. They'll want to talk to you about that. Yeah. Yeah.
Well, thank you, John.
Yeah, thank you very much.
Yeah.
Can you hear me and see my screen? Great, thank you. So hello everyone, and I wish I would be there in person to celebrate this milestone in Professor Agrawala's career, but unfortunately my visa expired, and you know visas these days take ample time to get, but here I am. So I'm going to talk about Dr. Ashok's contribution to location determination technologies. So I joined Professor Agrawala's group in 2000. During that time, they were working on the Rover technology, context-aware technologies. I think Christian is going to talk about it today, where we want to provide context-aware computations to the user. And of course, one of the most important context information is the location. And if you think about location, what comes to mind is GPS. However, GPS doesn't work indoors. So we needed a technology to work for localizing users and devices indoors. And at that time, of course, it wasn't that common. There were a number of technologies, but they needed huge infrastructure, special hardware, and so on. So we started looking into solutions to indoor localizations that can work with mobile devices. At that time, the radar technology, which presented Wi-Fi based localization, was just there as I joined the group in 2000. So radar was using a deterministic technique based on the received signal strengths for Wi-Fi access points. And we thought about and it was providing maybe 3 to 4 meter median error accuracy. So we thought about, can we do better? Can we get higher accuracy using other approaches? And this is where the Horus system came, which was my PhD topic. And we also worked on other indoor technologies for localization like pinpoint. And we introduced the concept of device-free localization, which I'm going to touch on my talk. So first, the Horus system was, as I mentioned, my main PhD topic. It's a Wi-Fi based system based on the received signal strength. It was the first probabilistic system and the second immediately after radar. And during the PhD, we managed to deploy the system and test it in different venues, as I will talk about. And we got a median accuracy of about 1 meter. We actually tested it in E.V. Williams building at that time. I collected the data myself and deployed the system, and the accuracy was amazing compared to the radar, as I mentioned, maybe 300 times better in accuracy. So the impact of Horus actually is still, till today, is still one of the most commonly used system for benchmarking location tracking systems for indoor environments. So researchers till today, I think I checked maybe yesterday or so, we have 150 citations just this year. And people refer to it when they want to compare to their system to some benchmark. And the way we thought about Horus and how we implemented is to identify the different issues that can affect the received signal strengths and then provide solutions to the different issues. And for that, we had an analysis where we proved, for example, that Horus is indeed better than radar under general assumptions. And as I mentioned, we did implement the system. We showed how to handle the correlation in the received signal strengths, where the norm was that if you use a probabilistic technique, you should assume independence. So we showed how to address the correlation and how to get the benefit of this processing to further enhance the accuracy of the system. So actually, it wasn't just the Horus system and its performance that exceeds any of the current system. Actually, it was a learning experience that I learned many things from Professor Agrawala. So one of the main things is that I remember our first meeting where I was describing my first approach, probabilistic approach to solve the Wi-Fi based localization based on received signal strengths. I had this nice complex system based on hidden Markov models where I have n states, each state has m observations, and very nice complicated analysis of the system and how we can get good results. And then Professor Agrawala asked me this question: why don't you just use a single state? And for me, it was just, what? Why a single state? If I can build a complicated system, why should I build a simple system? But actually, it turned out that this simple system is what was behind Horus, and that was one of the main reasons that it has its impact till today. So one thing is, don't always look for complicated systems. Maybe in some problems, complicated systems are worthwhile, but start thinking with very simple solution and see how can they perform, and do we need really a complicated system or not? Another thing is that actually Horus has a huge impact academically. It's not just papers. We have thousands of citations for the Horus papers. And as I mentioned, it's still one of the most used benchmarks for location tracking systems. But the other side is that it's a practical system. It has a value that we had different companies licensing it, like Fujitsu. For example, we have a startup companies based on ideas from the Horus system. And it also won the Invention of the Year award from the Office of Technology Commercialization at the University of Maryland. And actually, I found this plate where this is the plate we got as winners of the Invention of the Year award in 2003, Professor Agrawala and myself. Actually, you can see in the background, I found actually this template. This template was from the Mind Lab, which was established, as John mentioned, in 2000. In the same year, I joined Professor Agrawala's group. So it was actually a lab that had many projects, exciting projects for me and for many of my colleagues. So this was my main PhD topic. For the state of the art, actually, Professor Agrawala and myself worked on the idea of device-free localization, where we can track a person without him or her carrying any devices, just by analyzing their effect on the ambient signal strengths. At this point in time, this paper was a vision paper in Mobicom, which is a prestigious, highly prestigious conference. It was a vision paper in Mobicom, and it was state-of-the-art changing ideas. So till this point, all systems depends on using a chip or a device attached to the person or object you want to track. But we introduced the idea of device-free localization. Can I track a person without him or her carrying anything? So this is what we call device-free localization. It was well received, but actually it took the research community 6-7 years to just come to this idea and see that is a useful ideas. And actually, as of today, it is one of the most, the hottest ideas in location tracking and sensing in general. It has different names. Others have reused the same idea and built on our ideas. They use sensorless sensing, through the wall sensing, and many other terms, but actually it started from this idea of device-free localization in 2007, while I was still with Professor Agrawala's group. Other problems that are still hot and active in location tracking for those who are interested in pursuing a PhD. Actually, indoor localization is not yet a solved problem. The point that we have an indoor equivalent for GPS, this is the point we can say this problem is solved. And by this, I mean you can go to any building around the world, turn on your device, and you get your location in any building accurately in different floors. So actually, this is still not there. That's why indoor localization is a very challenging problem. And Professor Agrawala had this vision in 2000, where people were talking about GPS is there, it's a solved problem, we don't need to do research in location tracking. 3D localization actually is still an open problem for research, where you want to find not only your location on the map, but also in which floor in the building you are currently on. Recently, my group has started looking into how to use quantum computing in location tracking. Maybe 1 year, 2 years ago, if you ask me about quantum computing, I would say it's science fiction. It's far behind. It wouldn't happen recently, but actually we have papers this year where we implement our location tracking algorithms on real quantum computers. So if you are looking for ideas for your PhD, maybe take a look at quantum computing and how you can use it in your research area. We have a vision paper and publications. If you are interested, you can Google my name and the research group. So finally, and most importantly, during my PhD and beyond my PhD, I found Professor Agrawala to be not only a research advisor with a great mind and experience to learn from, but also a great friend that I can always ask about issues in my personal life and depend on the sincere and valuable advice I can get from him. So thank you, and looking forward to the next big milestone in your career. Thank you all.
We're going to change the order a little bit because Neha has it.
Thank you so much, Ashok, for introducing me. Okay. So so I had data science and machine learning at Common Room. You may not have heard about us. It's a 1-year-old startup. 2 days ago, we just won the Startup of the Year award at GeekWire, so pretty excited about it. What we do is we help companies or SaaS businesses understand what their community is talking. And in the meantime, the byproduct is to help them enable sales, customer support, like overall market fit, understanding what product they should build next. So a lot of interesting work that the company does. I graduated from Maryland. A little bit about myself. I was born and raised in Roorkee, India. It's funny that Amitabh's dad was my dad's professor. Yeah, so Amitabh is from Rookie as well. And I went to IIT Varanasi, came here and graduated in 2012. And I have been at Adobe, LinkedIn, and Uber before I joined Common Room. Yeah, so what inspired, and this is very timely, this is the what inspired me for my topic of PhD research. This is the famous map of A.V. Williams building, which me, Christian, Mustafa all used to map using our indoor location systems. And when I came here, for my master's, I was working on networks and working on different researches with Christian and other fellow PhD students on computer networks. And when I decided to pursue my PhD, I told something similar, but maybe in different words, that I can learn networks, but I don't think I can think in networks. So I told Dr. Agrawala this, and then he said, okay, why don't you stand here, pick up your own PhD topic? And that's where, I went for an internship. I talked to him, and then I went to KDD, thanks to Liz Kadur at that time, who added me as a volunteer. And then I got this idea of learning, working in multi-arm bandits, which is an online learning problem in the area of machine learning. So that excited me. And this was predated where AI, machine learning, everything became where it is right now. So a very exciting area. And he told, yeah, my PhD was in applied math, and sure, you can do that. So that was very exciting for me. Little did we know that it will become, so popular. So what was the summary outcome of my research? So just to talk a little bit about the Bayesian, bandit problem. So it is a problem of online learning. This is an octopus. So if you go playing different slot machines, if you go in a casino, for example, and you have only $10, then how can you play so that your reward is optimized while you're also kind of where your reward is optimized, just stopping there. And so one way would be you do some kind of an A/B test. So you play with one slot machine, like for once, and then maybe if there are two, then play the second one and see which is giving you a better return. The other option could be coming up with a strategy that lets you learn while you are also exploiting the knowledge that you gained in your last run. If it was a loss or a gain. So that's what multi-arm bandit does. It helps, it's an explore exploit strategy, which helps you decide what is the next action to take. It's a form of reinforcement learning. He helped me formulate the problem. A lot of, I know his specialization was network again, Professor. He kind of mentored me, and I was surprised every time. And I had a conversation with him. I had read papers, I had run data research, but what he brought to the table was so amazing from his work done so many years ago. So very interesting. So the PhD was able to establish Bayesian multi-banded strategy as one of the prominent strategies. So there's a lot of different works you could do, a lot of different metrics you could apply to do this explore exploit, but Bayesian was one of the techniques that I work extensively on, and it is one of the most used techniques these days for this problem and also for other problems that you're seeing in other areas. Again, this is K-means clustering. And I already briefly touched this topic that his own thesis was on clustering or related to clustering or something related. Okay, so maybe I got this wrong, but you did some work on that. Machine learning. Yes, so it was great. It was great. We had a really good time working on my thesis. What is the current status of my work? So it's a very active area of research. I've quoted here my friend Li Hong, who is actively working in this area. So for all the students who are here, Li Hong Li from Amazon Sciences, he's actively working on multi-arm banded research right now. Amazon is very well positioned to do that because they have a lot of returning customers. Right. So a lot of Royal customers, a lot of us are Amazon Prime members, as I believe. And so the idea is, again, if you are coming back, then we as a company or we don't just want to predict the machine or the oracle that what you will do next or label you as a churn customer or as a high value customer, to also lead you to a path to be more successful on the platform. And that's what reinforcement learning or multi-arm bandit is all about, seeing the long term. And then not nudging, but taking you to a more successful path. And again, nudging has a lot of negative connotations to it. It's a challenging problem in coding Li Hong here, but it is super interesting and super useful. And again, applying, if you have enough data, then a lot of good outcomes can come out of it. Another thing that I have personally worked on in my previous job at LinkedIn was customer journey optimization. So again, applying bandits there, or reinforcement learning, where we try to understand when a customer, again, this is more LinkedIn business to business, not the LinkedIn kind of what we see on the product, but LinkedIn sells products for job seekers or for paid customers, which are actually other businesses who post ads or who post their jobs on LinkedIn. And what we are personally interested there is to understand whether, say, IBM, for example, is about to turn on the LinkedIn platform. They are about to kind of take off their HR from our platform. And so we try to predict that, and we try to understand where they are on their customer journey. So a lot of interesting applications of this area. And what I do now, I know these are the set of questions Ashok sent me, and I try to stick to it, but it's great. So what we do at Common Room currently now, I lead their machine learning group, and we do everything. We do everything from data foundations to product analytics to product intelligence, customer optimization, A/B testing, causal analysis. So a lot of good work. It's a very small team. So a lot of students here, we're open for internships and full-time hiring. So it's a great place to be. And if you know, only 2% VC-led companies are female-led. So my company, the CEO is Linda Lian. Yeah, so it's a fun place to be. And thank you, Dr. Agrawala. This is a picture of him visiting us in Bay Area. And this was a personal trip, which I thought, but this was also a trip to raise funds for the AREEP Center. So yes, he not only, like to Samir's point, he came and he was able to kind of gather together the alumni. So thank you so much. Thank you, everyone.
Wow, we could be here listening to all these stories, man. I want to learn more, right? In every talk, I want to say, I want to learn more. I could be here, but I guess you might be getting called from me so you can learn more. The next one, I'm going in the backward direction. We skipped over Christopher Landover. Christopher Landover is an eminent mathematician. He's done extension work in complex system, adaptive system, self-improving system, but he also holds a patent with Ashok Agrawala and his student Sung Lee on cyclone technology. And we're going to learn about that from Christopher. Christopher, can you hear me? Hear us?
I looked at this list of speakers and noticed I'm the only one who was not a student of Ashok's. On the other hand, anyone who ever worked with Ashok learned something. So in a non-technical sense, I was a student. I learned many things about the way he thinks about these systems. I am a mathematician, PhD Caltech, early 70s. So I met Ashok when he was a contractor working for DARPA, on a DARPA program with Dr. Kirsty Bellman, who you heard from earlier. I was intrigued from the beginning with his notions of time. He had a very different view of what time is and how it works from anything I had encountered. He and I talked about what that might mean, and particularly about what that could mean for real-time systems. I saw an implementation that he had done of Maruti, which was a real-time operating system, which was fascinating. It led to the notion of a smooth, not just a smooth flow of information, but a constant rate flow of information. And he asked me a question: could you make an internet synchronous? Now, historically, the internet was not synchronous because the reliability of the components and the links was not as high. The ability of systems to react to data coming in was not very high. This was, as you No, the internet was developed in the mid 60s. And when I talked with Ashok, it was in the mid 90s. The systems were faster, the links were faster, they were all more reliable, and it made sense to consider a synchronous network. That was called Cyclone. In a synchronous network, the arrival of data was signaled by when it arrived, not by what was in it. So packet headers, so to speak, were not required, or at least not the same kind of headers. What we did was to design a system that would allow a completely synchronous communication mechanism for all of the nodes. Today, streaming, voice over IP, both require not just a smooth flow of information, but a constant rate flow of information, for which a synchronous underpinning would be really, really useful. But they have spent an enormous amount of effort trying to force synchrony on a system that is fundamentally asynchronous. Cyclone could change that, could have changed that. My contribution, after many, many difficult questions from Ashok, was to build a time synchronization algorithm. So the issue was, and again, something that GPS does now, but GPS does not have to also communicate data streams in addition to synchronizing time. I built a time synchronizer. That was the mathematics part of it. But the whole process was really remarkable because I had a very long sequence of very difficult questions from Ashok about how it can work, how it could work, how it should work, and what to do about it. That was a marvelous experience. And this was 25 years ago now. It was really wonderful. And I haven't had any such response, any such interaction with another academic person since. So I'm very pleased, very thankful for those hard questions. That's it, I'm done.
Thank you. Thank you. Thank you. What was the quote that you were saying that Sung Lee's committee said? Those were fascinating about that.
Yes. Can he hear from this microphone?
I think he can.
Yeah.
Yeah,
You can also tap the puck on your table if you want to talk.
you can just tap and talk.
Yeah, Ashok.
Hi. Chris, it's so good to see you. Anyway, the comment that Professor Jeff Hollingsworth made was at Sung Lee's PhD defense on Cyclone was that this is the most effective use of linear algebra he had seen in any PhD dissertation.
Yep.
Effectively, that's what we are doing, using linear algebra kinds of things in the formulation, because what we are controlling was we'll receive packets at any time, but we'll control when we send the packets. And the delay we were controlling, and that's how we were synchronizing everything. And instead of using networks like Sonnet, atomic clock at $500,000 per node or whatever the cost was, use a $10 crystal clock, waste 1% of the bandwidth, and still achieve synchrony. Anyway.
Pretty fascinating. Thank you.
Fascinating.
Thank you, guys. Thank you. It's like it reminds me of the traffic lights at the on ramps, right? That same concept, similar concept. Okay. Next up is Christian Almazan. Yep, Christian, come on up. Christian is a software engineer, and he said he's been captivated by context-aware computing ever since his graduate student day. He's currently working as a senior software engineer at SSB Innovation in Aurora, Colorado.
All right, thank you, Ashok. So today I'd like to talk about contextual computing. So we've heard a lot about time. We heard a little about location with Dr. Youssef. How do you actually use all that now? When I was doing my PhD in 2000, between 2013 and 2010, there weren't so many devices out there as we have today. And I'll talk a little bit about that in a second. Before I get to that, one piece of context that we really focus in on is time. So one of the lessons that Ashok taught me, I call him Dr. Agrawala or Ashok, it depends on the time of day, I guess. How long does it take to prepare a presentation? Yeah, he taught me a very important lesson. So he actually asked me a question. He actually asked me that question, and I guessed completely wrong. So, and this is an important lesson for people, I guess the students over there, so they're sitting all the way in the back. How long does it take to prepare a presentation? So how long does it take to prepare a 1-minute presentation, also known as the elevator pitch? You need a lot of planning for the elevator pitch, because how do you make an impression in such a small amount of time? How long does it take to prepare a presentation for a day? His answer was, when do I start? Because you don't really need to prepare that much if you have a lot of time. There's a lot of room for discussion. And then the bottom one is actually mine. 8 minutes. It's somewhere in between. I can tell you it probably took me about 8 hours to write this presentation because I was doing other things at the same time. But I didn't really want to get this wrong because it's Dr. Agrawala's 50th anniversary. So I spent a bit amount of time actually just thinking about what do I want to present to everyone here. I guess one of the questions is, what got me excited into context-aware computing? When I was an undergrad at NYU, I joined a research group and wanted to explore what research actually involved. During that time, a new faculty member joined. I never worked with him. I never had a class with him, but I was fascinated by the work he was doing to support pervasive computing. And when people think of pervasive computing, they think of Mark Weiser's article in Scientific American in 1991, The Computer for the 21st Century. That article basically asked, how do computers and technology become so pervasive that they just disappear into the background in the environment? I can see, when I used to teach a lot and give a lot of presentation, there are people in the background just looking at their cell phones. That's not really pervasive because it's not really in the background. You're actually actively involved looking at something. But, this morning, there are 6,000 sensors in this building. Do we actually know what all of them do? Clearly Ashok's group does now. So how do you use that technology to just make lives better for everyone? One of the key things I learned from Dr. Agrawala was, how do we use technology to improve the quality of life for everyone around us? Also, while I was an undergrad, I read an article in IEEE Computer called Rover, Scalable Location-Aware Computing. Dr. Youssef spoke about that a little bit, and we'll get to that in a second because that was the main focus of my research. So how did I actually come about meeting Dr. Agrawala? So this class has been mentioned a few times. In fall of 2003, I took the class. It's called Information-Centric Design of Systems. I can tell you about half that class that year was on stochastic and probabilistic models. And the rest of it was, talk about some systems that you're interested in. I think that course has actually evolved over time to be more about context-aware computing. So I actually gave a presentation on pervasive computing during the class, and he invited me to work with his lab, the Mind Lab. So I had the opportunity and the privilege to work with a lot of people at the university, as well as industry partners on context-aware computing, location determination technologies, and wireless technologies. Being exposed to various industries, that really helped me, grow as a person. I still use a lot of the lessons today. I mentor a lot of junior software engineers, and I think, what did Dr. Agrawala teach me that I can teach them? So I always keep that in the back of my mind. Even if I don't think that Dr. Agrawala said something, it probably actually came from him. So moving along in my career, I always asked, what context do I need to solve a problem? I guess, during my time here, one of the things that I really enjoyed doing actually was Maryland days. So there's a picture of us at the tent in Maryland at a Maryland day. This is the infamous Maryland day, which was super hot, super muggy. And I think that's the day we discovered Dr. Agrawala has his own self-maintaining air conditioning system inside of himself. He's wearing, if you notice, he's wearing like a collared shirt. He's not sweating or anything. And the rest of us are like ready to just hose each other down. So that was like one of the hottest days. Being at Mine Lab, we got to work with a lot of partners. So that's then Police Chief Jay Gruber and then President Moat, yes, with Dr. Agrawala, just showing the infancy of what came to be known as emergency. My mom was actually rummaging through some of the old materials we had, just trying to clean up the house a little bit. And she found a Diamondback we actually kept. So I actually had her take a picture of it, and it's right here. So there's a lot of articles out there on a lot of the work he's done with trying to improve public safety. And there's a couple of screenshots and a couple of posters we actually did. So back to my work. So I actually defended my thesis on April 21st of 2010 on a thesis called Rover, Architectural Support for Exposing and Using Context. So I took a step back and identified the fundamental elements of context. So when we think of context, it's basically time, location, and identity. And then there's other things in there like temperature, how the flow rate of something, and so on and so forth. And how does context relate to everything? So I ask these questions every day in my life, actually. So it's not just research that I apply this to. It's also, what am I doing with different things? I built a context-aware platform called Rover, which was extended later, and I'll get to that in the next slide. So how can developers use context effectively in development? In 2010, there are some systems coming up and a lot of frameworks, but not as much as we have today. 12 years is a long time in the computer industry. And then the second question I also asked was, how can we support heterogeneous communication platforms? I still think that's a problem today because every time someone pops up with like a new standard like gRPC, another one's going to pop up like next year. And then suddenly we're supporting so many different things. I also came up with the concept of Rover Ecosystem. So how do we logically organize similar entities together? So in one system, you have like the campus community who's concerned about, grades and, what's playing at the Hoff Theater versus, the public safety aspect and, what they're concerned with. So how do you just relate those two? I'm going to skip over this slide for a second because I actually meant to put that last. Okay. So there was a lot of research after me with at least 4 theses that built off of it. So you had Rover 2, shrink wrap security, proactive computing, and then Rover 3, which Nick Gramsci will be talking about. There's a lot of context-aware computing that's going on today. It's not just the overall context-aware systems, it's also the individual pieces of context-aware computing. The future is all around us for context-aware computing. So from 2010 to 2022, there's a lot more devices out there that we can actually use. And what makes this field exciting? You can make an immediate impact on the real world problems. For instance, I worked on a project providing aid to veterans with TBI, where they actually wear location tags and you can, activate nearby screens. There's also linking different contexts together, such as making sure your tool is torquing the right screws on your side curtain airbags with the right angle and so on and so forth. And then I guess let me just go back here and just say, Professor Agrawala's guidance, he's more than just an advisor. He's a friend with lifelong advice. He wasn't there for just the successes, but he also helped all of us when we needed assistance. He guided me through the whole entire process through research and being an effective communicator, through writing and presentations, as well as providing me exposure to other fields. And he does that effectively for everyone that he encounters. So thank you for the time and the invitation to speak. And thank you, Dr. Agrawala, for everything that you've done for all of us.
Thank you. Next, we actually have 2 speakers. One I have recorded and one in live, and then Professor Agrawala is going to wrap up. It'll take a few minutes, just 5 minutes to wrap up. So next I have Nick Gramsci. Nick is currently working as a principal software development engineer at Microsoft in Great Falls, Virginia. Before that, he worked as software engineer, managed positions at AWS. So yesterday you saw it. I don't know, some of you saw it. Nick is coaching his kids at Little League today. I couldn't get out of that game, so he's sent a recorded presentation.
Congratulations, Dr. Agrawala. 50 years. That is a long time of inspiring and challenging minds and revolutionizing the field of computer science. Or in your words, corrupting the minds of the youth. I'm sorry I couldn't be there today. I too am corrupting the minds of the youth as I have our last regular season Little League game with 11 9-year-olds. And yes, I interweave some of the learnings from you on the baseball field with them. I don't know if you know this, but I almost failed out of Maryland my first semester. I was a new grad student after an 8-year break from school. Though I was not lacking in motivation, your information-centric computer design class gave me even more inspiration and drive and passion in my grad school pursuit. You did manage to corrupt me into pursuing the PhD, and it was a journey I am ever thankful for. I enjoyed our many, many long and deep philosophical conversations in your office about what information really is and how we as humans process and manage information. This exploration of information management and the ability to abstract away how humans process it was key into exploring how to really manage context and relevant information. As we dug deeper into the various ways, the clarity around the possibilities to completely rethink how we manage context and general programming models was quite enlightening to me. It was then that the concept of an automatic dynamic information ontology was born. I really enjoyed exploring how we managed to create this new way of moving the modeling aspects into the information model itself. Putting it to work in the Rover 3 prototype was quite fascinating, and I gained just as much about how to manage and accomplish something challenging, new, and abstract as I did in our exploration of new ways to manage information and context. I am ever thankful for your role in this research. Your intellectual stimulation as we explored this space was the catalyst to surfacing new ways of thinking. The types of questions you would ask really allowed us to explore the space in the best way possible. There was never a wrong answer as we kept imagining the realm of possibilities. When it came time to develop the prototype and putting our thoughts and philosophies into practice, your guidance and mentorship was profound. You kept me grounded in what was needed for the PhD while still allowing my thoughts and dreams to soar. Your coaching through the process was instrumental. I've been an athlete all my life, and this was the first time I had someone coach me in something other than running. The long journey down the PhD road required a lot of energy and time from you, and I acknowledge that this was one of the best coaching experiences I have lived through. While not germane to the PhD, we did spend a lot of time talking about the world and life in general. That human touch really rounded out the experience, and there are many lasting memories about such talks that I will always cherish. Lastly, your positive attitude and support kept me pushing through the process. Getting a PhD is never an easy task. Working full-time with 2 and then 3 kids made my pursuit tough, but you were my biggest cheerleader during this time. You kept inspiring me, motivating me, encouraging me, and kept me positive through this journey. I found myself lucky that I now work in one of the biggest context-aware systems in the world, yet I still don't get to push the envelope like we did during my research. I'm currently at Microsoft, and I get to see one of the biggest information management systems in the world with Exchange Online. We have built a fascinating system where we have a context management system on top of some of the world's largest and complex databases. The result is a portfolio of thousands of software systems that provide thousands of user experiences based on every aspect of the information at hand. Keeping things private on a per user basis, we provide many search, AI, social networking, and context enrichment experiences across all the collaboration tools like email, chat, and document creation. It's fascinating to see one of the world's largest uses of a context-aware system. Yet I still think the industry is light years away from some of the things we explored and proved. What I don't see anywhere, including at Microsoft, is a very generic approach to managing context and relevant information, similar to how you and I envisioned it. So many systems are built for specific use cases, and I still believe there's a way to create a generic information management system to handle relevant information. Rather than write scenario-based systems, I believe we can model the relevance in the information itself and reduce the complexity of the systems before us. If we can inspire someone to continue the work of a dynamic information ontology, I believe there's a lot to gain. A good approach might be to show how Rover 3 or a similar system can be put into practice. Much of what we did was theory, so simplifying the approach and proving that our practice works well at scale can not only be a good PhD project, but potentially a great business opportunity. Anyway, I've gone on to pontificating about crazy ideas and proposing lofty things for someone foolish enough to pursue. I guess you've taught me quite well. Once again, congratulations on 50 years. I know I'm just one of many people who are ever grateful for your insight, contributions, and support along the way. Thank you.
So last speaker is Faizan Wazid, and now you're looking at the future. You know, so that was we can still call Nick also passed because he's old graduate, but there's a new graduate, number 53 probably, right? 53 probably would be the guy here. So Mr. 53, he's currently PhD student in computer science. He's minding the mind lab these days, among some other folks that are doing that. And Faizan?
Thank you.
Please keep us tight so
yes.
that we kind of run late.
Of course. Yes, thank you, everyone. Thank you for coming here today. My name is Faizan. I just want to start talking a little bit first about the Mind Lab today. Before I started, I actually went into, so I started my program as a master's student. And by the time I finished, I was just ready to leave. I was done. But as fate would have it, I ended up taking Professor Agrawala's class, Contextual Systems, in my last semester. And then I would come into his office just to talk a little bit about the coursework. And then that turned into 1 to 2 hour discussions about everything else. And so by the end of the semester, I was convinced that I was going to come back to do a PhD. And so here we are today. And so I think over the years, I started in 2018, and along with Mara and myself, we've been coordinating the activities of the Mind Lab. We have grown quite a bit in terms of all the activities that we've been doing and the student outreach, particularly working very closely with Dr. Agrawala to kind of look at the vision of what education is. How do we do outreach? How do we gather students to come in and engage in research? Because for a majority of these students, this is their first time being exposed to research. So they may have had a bad experience. We want to try to correct some of these things, and then to also engage with industry collaborators from the software development side, from engineering and everything, and to just kind of have this conducive environment where people can think freely and to be able to engage in practical work. And so in terms of the projects, what are we actually working on? I listed 5 here, just more, I guess, the primary few. Context-aware systems you've already heard about, but I'll focus specifically on numbers 1 and 2, building and breathing analytics. And this is the kind of keyword we've given it because we've been looking at these problems more from the engineering computer science lens, and they are interesting in and of themselves. So for building analytics, the goal is to try to model this EREEP center and then project it also with other, commercial buildings and residential buildings. So, for example, if you can imagine a smart home on a small scale, but then if you take that scale and then magnify it to thousands of concurrent individuals coming in, whether they're professors, whether they're industry specialists or whomever, to be able to look at the kind of activities that they do and try to optimize the building given that sort of information. So if you have for this building particularly, you have over 6,000 sensors. How do you actually make use of that data and how do you use it productively? Can you determine things like when you have temperature, when you have CO2 levels, can you optimize in terms of maybe schedules, how people are coming in, when should you set the temperatures at certain times? An example of some of the sensors here, you can see we have access to look at the airflow ducts, and we have sensor information coming in for airflow, for temperature, for chiller and heat generation. This is all modeled in 3D, and so we can kind of project it onto that landscape and try to put everything together. And some of the things that we've done so far are working with our collaborators, whom you've probably have met today, looking at this information and for example, looking at the comfort index, which is an ASHRAE defined standard to determine if the room is on par with the things that if a person would find comfortable to sit in and to work in. Energy consumption as a function of the airflow into the room, how long it takes to heat it up and cool it down. Plenty of things that we also want to do. Model dynamic changes. So for example, Professor Agrawala's main experience in control systems is very handy and relevant here because a building is, it's a massively complex system. So taking this data and then looking at the engineering side, the physics of it, and to kind of drive that towards a more complex scalable solution. And also AR and VR or XR for example, on-site maintenance. I kind of joke about calling it a stud finder, but if you imagine having a VR headset or some type of AR phone, can you look at the beams, the chiller beams behind the wall and see the temperature of the air, the flow rate behind them, and use that as a way to do on-site maintenance or any other type of activities that could lead to. So breathing, I've been spending most of my time on this particular project. There's plenty to read here. I don't think you have to. Basic idea is, if you imagine, we don't really necessarily think about our breathing so much, but if you were to think, if you take a deep breath, right, you might have moments where you just don't breathe at all for maybe a few seconds or maybe up to a minute. But then you also have moments where you have shallow breathing. So these are important in trying to determine the kind of state a person is in. So you can break this down into, if you were to look at each individual breath that we take throughout the course of a day, can we come up with some measure of what normal is for a person? And how does this reflect onto respiratory illnesses, things that we're familiar with, other respiratory phenomena such as asthma and apnea. And the reason why this is important is this type of study really actually hasn't been done. The physiological aspects of it is basically that if you go into a doctor's office and you start looking, they basically sit you down and you take this waveform, you clean it up and you smooth it, so you lose the raw features of the breath. So what we want to do is take that, collect it, and try to determine some patterns around what normalcy is, the deviations from normal, and doing this breath by breath, given the kind of situation that we want to work with, is the best way to approach this. So how do we actually do that? Well, one of the things that we do is we use this Spire tag. It's a small little tag you place on the waistband, and that determines, that detects the force data, which is a sensor data along with the accelerometers. And if you were to take that data for the course of an entire day, 24 hours, recording at 25 Hertz sampling rate, you get 2.1 million samples. And that's what it looks like, with the blue being the force, the respiration, the XYZ being your accelerometers. And then you can zoom in very finely to see this is what the 30-second respiration looks like. So what do we do with that? Well, first thing is, if you have all this data, right, the main focus of Professor Agrawala's approach is you just stare at the problem for as long as you can until you start to see the patterns there. And this is actually very critical. This is very important. And I realized very early on is that as we start doing these things, we have these discussions, if you walk into his office, you think you have a simple question, it kind of blows up into a significantly more complex question that you didn't really think about. And so even though everyone has said, Professor Agrawala loves his coffee, it's true, but also I don't think I've heard anyone say so far is that sometimes you actually need it. You come in, think you have a simple question, and then it comes into, really, I think the crux of it is that to get to the simplicity, you have to talk through the complexity, right? And that's, I think, one of the main key things that Professor Agrawala has taught me, and I'm very appreciative of that. And so in this problem in particular, we take the whole day, we look at the sleep period. From the sleep period, we identify the different lay positions as the person is sitting, laying down in their bed. We segment it into individual breaths. We then develop features on these breaths. And then we end up with a feature vector representing the breath. And then from there, we were to take that data and look at what a sick person and non-sick person, for the same person, you have sick and non-sick data. And if you project it into a two-dimensional space, you can see some of the interesting things here is that normalcy here is actually much more varied. The breath pattern for normalcy is much more varied than it would be if the person is sick. Our intuition going into this problem was that it was actually the reverse. So, having these discussions, forming the hypotheses around them, and to be able to go through the steps and processes to solve these problems definitely comes from the engagement and the kind of work that we've been doing. And for him to pick my brain until I say, I don't know anymore. So plenty of things we've done to date. I will skip over this. But the end of it is that first, congratulations, Dr. Agrawala. Thank you for your ongoing support. Thank you for having me, and all the best for all the work that we'll continue to do.
How long we come? Come on. Man, good. We're coming from all this time to time of our breath, huh? Quite a journey here. Quite a journey here. Ashok, just come on. I don't know how you can summarize this thing, or what your perspective would be in 5 minutes or whatever time you need to take to.
All I have to do is to speak faster like an Indian and just increase the bandwidth. Well, folks, this period since yesterday has been a period of big fuss about 50 years. But I don't know what the fuss is about, because the problems I couldn't understand or solve yesterday, I can't solve today. These are still the problems, but the question you can raise is, what are the kind of problems that I'm worrying about today? So let me share that a little bit. Some of it is based on intuitive insights. Some is based on pulling things out of head, whatever. I sincerely believe at the moment that we have seen the equivalence of energy and matter, but there are two fundamental building blocks of the whole creation: information and energy. And then you can talk about what kind of things are being done. Each of us have some intuitive insight as to what information is all about. Has it been defined anywhere? Forget about Shannon's information theory. It only talks about how you move bits. Forget about most of the other things that people call information. I'm appealing to what you and I understand as information. And it was an observation that we made, I think Ron was involved in that too at one time, that you have to start with the distinction between information and its representation. And any and everything that we manipulate in the physical world is the representation and not the information itself. So I want to add 2 and 2. First of all, how many ways in which I can represent 2? Is there countable infinite or somewhere close to that? I can lift 2 fingers. I can go to the board and put some ink on a particular pattern. I can go represent it as a 1, 0, change the basis, represent it in some other form. Not just that, some charge somewhere, some other charge somewhere. That's a 2. I want to add 2 and 3. Have a representation of 2 in these charges somewhere. Representation of 3 as charges somewhere. Pass it through some circuit, out comes some other representation. And I say, I've added. How have I added? Because the kinds of manipulation that we wanted to do at information level, I was doing at the representation level. And I would submit to you that only those manipulations of representations that make sense at the information level are meaningful, others are not. So we can go and pass all kinds of garbage, good old garbage in, garbage out phenomenon. Ultimate user of information is you, and you and I can only do it in our head. You can go back to philosophy, you can go back to mythologies, you can go back to metaphysics, whatever kinds of things. And I'm trying to go to all of them. Now, I'm going to walk you through a very simple kind of exercise and leave you to think about that. I submitted to you that any and every piece of information, what we call information in IT field, is a representation. And a representation in general, not in general, in particular, is created by an arrangement of either energy or matter. So I take chalk dust, put it in a particular pattern, it is 2. The same chalk dust in a different pattern is 3. It's a pattern that matters. Same kind of thing you can apply. And I would submit to you that to this day, I have not found a contradiction to that. Okay? Now, if you start out that I have the representation which I have to keep in this arrangement form, I need a container in which I have to keep that arrangement. Until I go and peek inside the container, I cannot know what the information is. I know where the container is. I can make a path to the container, but not to the content. What is the implication? In physical world, you can never construct a content addressable memory. You can fake it, you can index it, you can do parallel searches, all that kind of thing. But at the base of it, you cannot construct content addressable memory. Now, when you and I think, do we say it's stored here or here? On the basis, do we access that on the basis of coordinate? If you and I access our information that we have stored, I wouldn't say in brain or mind or wherever else, that we have stored and have access to on the basis of content, it cannot be in the physical form. What form is it in? I'll leave you at that. Thank you so much. And if you have any answers, come back and see me. I am seriously pursuing this, and I can go into all kinds of details of this, but I won't keep you, I won't come between you and your dessert, which is waiting outside. Okay? A lot of work has gone on in this kind of thing. This is my passion now for last over 10 years, 15 years, something like that. So I've taken it down the rabbit hole in a variety of ways. Thank you so much. I really, really am honored and grateful that you took the time to spend here with me, with us. And really, none of that would have been possible, feasible, doable without Ming and Ashok and the team that they put together with Todd, with Miriam, with Richa, and a whole bunch of others who were in the background. Thank you so much once again. Thank you very much.